We now want to discuss couple of examples on electric potential. So in the first example, we want to compute the potential at say a distance r of 9 centimeters from some charge q. So q is given as 4 into 10 to power of minus 7 coulombs. So let us draw this. So we want to find electric potential at this point P, and we have a charge here q, and the distance of point P from charge q is r. So potential at point P, so this is electric potential. So we know the formula is kq over r as we discussed in previous lecture. K is 9 into 10 to power of 9, q is given as 4 into 10 to power of minus 7, and r is 9 into 10 to power minus 2 meters. So this will give you 4 into 10 to power of 4 volts as the answer. Now you notice that this potential is a scalar. So this potential V is a scalar. So we can add potential up due to different charges. So we can add a potential due to different charges. So different charges are having different potentials at a particular point P, and we can add up all these potentials to get the total potential at point P. So this will be given as, now K will be constant everywhere, so K comes out. So you sum over all Qi over Ri. So let us give an example to understand this. So say at this point in the Cartesian plane, you have 2 microcoulomb at point 0, 0. Then you have 3 microcoulomb at point 2, 0. Then you have minus 4 microcoulomb at 1, 1. And we have this point P right here at 1, 0. That is on the x-axis. So we want to find the potential at point P. So the question is that we need to compute potential at point P. So potential at point P is because of 3 different charges, and we have to use the summation formula now. So K times first charge divided by distance of point P from the first charge, second charge divided by distance of point P from the second charge, and finally Q3 over R3, that is third charge divided by distance from the third charge. So let us take this as Q1 as 2 microcoulomb. So the distance from point P is exactly 1. So this is R1. This we take as Q2 as 3 coulomb, and it is a distance 1 from point P. So this is R2. And we take Q3 as minus 4 coulomb, and the distance from point P of charge 3 is just 1, which is R3. So now you just plug the values in. You get K times 2 by 1 plus 3 by 1, then Q3 is minus 4 divided by R3, which is 1. So this just gives you K. So this is K times 1 microcoulomb. So 5 minus 4 is 1. Everything is in microcoulomb. K is 9 times 10 to the power of 9, and 1 microcoulomb is 1 into 10 to the power of minus 6 coulomb. So this gives you 9 into 10 to the power of 3 volts. Now we want to talk about work done. So that is work done in moving a charge into a system where there is a existing electric potential. So let us write this down. So say you are given a potential of a system. So there is a system which has a potential, and say we are talking about particular point P, just like in our example. So the work done to bring a charge Q into this system which has electric potential is given as, work done is Q times the potential at point P. So this is potential at point P. Again, this formula comes from the fact that work done is same as potential energy of the system, and potential energy of the system we defined as Q times electric potential before. So let us write this down. Potential energy of the system we defined as U, and U was Q times V of P, and potential energy of the system is also equal to work. So for example, in the just example we have covered, so say you bring a charge to point P and this charge is of 2 microcoulombs and the point P is exactly this point here. So you bring the charge of 2 microcoulombs here at this point P. Now work done will be Q times the potential at the point. So 2 microcoulomb is 2 into 10 to power of minus 6 times 9 into 10 to power of 3. So this is equal to 18 into 10 to power of minus 3 joules. So that is the work done in bringing a 2 microcoulomb charge to point P.